Welcome everyone to Remarkable Insights. My name is Pete Horsley. I'm the founder of Remarkable. We are an early stage tech accelerator for startups that are creating technology for disability. We are part of Cerebral Palsy Alliance, and we have our principal partner is iCare, and we have partnerships with Telstra, Vivcourt and Microsoft as well. Remarkable is where hopefully technology meets human potential, and we see a real gap that exists in the place that technology can play in the lives of people with disability. We mainly do that through a 14-week accelerator program where we support early stage startups commercializing their technology and getting them on the path to getting their technology into the hands of the people that need it most. I want to acknowledge that I'm on the land of the Guringai people. This is their land. It was never ceded, and it's always sacred, and I pay my respects to elders past, present and emerging. And to wherever you are joining us from as well, and the traditional lands that you're meeting on, also pay my respects to elders past and present there also. Also pay my respects to the disability advocates who have come before us, have fought for the rights of people with disability over many, many decades, and we stand on their shoulders now in doing the work that we do. We have both the privilege and a responsibility because of the work that they've done. So today's conversation about Remarkable Insights conversation is about brain-computer interface. And we know that there's significant opportunity to leverage technical innovation to drive an inclusive future. And we want to ask the question about who's getting left behind as technology accelerates around us. And we want to ask as well, how can we start to create an inclusive now rather than just an inclusive future? So for anyone wanting to join this conversation on social media, please use our social media handles at Remarkable Tech, and also use the hashtag Remarkable Insights. The event has live captioning by Otter AI. You can make use of that using the live transcript. We also have a separate AI transcript that you can click on your screen as well. And today we also have sign interpretation by Taryn Coswello, so welcome Taryn as well. Today we're joined by Nick Opie from Synchron, presently in lockdown in Melbourne, Australia. We've got Beata Jasarowicz from Neuralink in San Francisco, and Zubi Onwuta from Think and Zoom in Austin, Texas. Welcome to each of you. Today, some of the people on this call are very familiar with what brain-computer interface is. But for some of us, it might be relatively new. So I'm going to ask Beata, if you've been at the forefront of BCI for quite some time, working with a number of different organisations, including someone who's a good friend of Cerebral Palsy Alliance and Remarkable, Lee Hochberg and the team at BrainGate. So do you mind just giving us an explanation of what BCI is, please?
I would be happy to. Can you guys see my slides okay? Hear me all right?
We can.
Okay. So let's see. I'm sorry, it's got this live captioning thing at the top. There we go. Okay. So just a brief overview of motor brain-computer interfaces, which are meant to help people with paralysis to be able to control their environment and communicate. So like every cell in your body, brain cells, also called neurons, have a voltage across their membrane. And when they communicate with one another, they rapidly change their voltage over the course of just a millisecond or so. And we can spy on these so-called action potentials, or the firing of these neurons, to try to interpret what the brain is trying, or what the brain indicates that the person's movement intention is at any given moment in time. For example, so this is a picture of a human brain on the top left here, where the left side is the front and the right side is the back. And the red strip there, the strip labeled in red, is called the motor cortex. This is the part of the brain that controls voluntary movement. Different parts of the motor cortex, if you look at this blown up cross section, represent different parts of the body. So if you record from a neuron in the hand or arm area of motor cortex, you might find activity that represents the person wanting to make particular movements of the hand or arm. And here's an example of a neuron that we recorded when I was at BrainGate from participant Kathy Hutchinson. The technician is going to be asking her to imagine that she's opening and closing her hand, and see if you can hear a difference in the activity of this neuron. It's going to sound like little popping sounds.
Relax. Now imagine you're opening your hand. Relax. Close your hand. Relax. Open your hand.
So you can tell whenever the person is imagining opening her hand, the neuron kind of goes crazy. And when she imagines closing it, the neuron gets very quiet. And then with relax, it's somewhere in between. So you can take a neuron like this and just look at its firing rate in small windows of time and use that information to open and close a prosthetic hand, for example, just by asking the person to imagine that they're opening and closing their own hand. So here's a video of us doing that with another BrainGate participant, Matt Nagel.
Close. Holy shit. Open. Close. Nice. Open.
So that's a very basic example of a brain-computer interface. But other neurons in motor cortex have encoding for particular imagined movements in different directions in space. So for example, one neuron might encode movements, imagined leftward movements. Another neuron might increase its firing rate when the person imagines moving their hand up. And if you record from a lot of neurons at the same time, which a lot of brain-computer interfaces do, and you know the preferred directions of all of the different neurons that you're recording from, you can look at their firing rates at each moment in time and figure out from the pattern across the neurons which direction the person intends to move. And then use that movement information that you've decoded to, for example, move a computer cursor on a computer screen. And this is the basic explanation or the intuition for how a brain-computer interface works. And of course, you can use that to allow a person with paralysis to point and to basically use a point and click mouse with her brain as though she were controlling an actual computer mouse. And this is another BrainGate participant, T6, who is typing an email to my colleague, Paul Nuyijukian, using a brain-computer interface. And then just for context, at BrainGate, or sorry, at Neuralink, where I currently am, we're trying to make a fully implantable and cosmetically invisible brain-computer interface with lots and lots of channels that will allow a person to be able to control devices in a very similar way, just by thinking about how they want to move. That's the end of my little intro. I will stop sharing my screen.
Thank you so much. You should be a teacher, Beata. That's brilliant. I feel like
Thank you.
I feel like we have a really good base understanding of the kind of technology we're talking about here. And just to give some warning to our participants today that that we probably might also be mentioning other things like EEG and fMRI, intercortical, neuroprosthetics, and other kind of terminologies. Hopefully, we'll try and explain those if we do mention those on the way through. So we know that BCI isn't necessarily kind of reading our thoughts, but it's reading the brain's activity when there's intentional thought, typically towards a physical activity. I want us first to explore the use of some of these cases, picking up the signals and then using them to control something outside the body. So Nick, firstly, congratulations on the $40 million Series B capital raise earlier this year. And already you've been doing human trials in Australia, but I know that you've just started or just got approvals for human trials in the US as well. So huge steps towards your own commercialization. So congratulations for that. What excites you about the potential of this technology, particularly for those people who might be living with a disability?
Yeah, I think it's just fascinating how the field's grown. Certainly, from some of the work Beata mentioned in BrainGate back in the day, the ability to access information from within the brain, extract it, and then convert it into signals that can be used by people with paralysis to control computers or robotic hands or vehicles being robots and wheelchairs and so forth. It is just incredible, and it's really fantastic to see the field progress to a stage where it's starting to turn from early stage research showing that it's feasible and possible to things like what we're doing, where it's being implanted into people and being used by them to enhance their quality of life. And I think it's amazing to watch the progression, and there's early stages, a long way to go, but it's fascinating to watch.
Brilliant. And Zubi, you didn't start your career kind of in this space. You kind of came to this technology through a slightly different track. Can you tell us the story of how you started working with BCI?
Sure. Thanks so much, Pete, and thanks everybody for being here. So yeah, I'm currently in Austin, Texas, USA, and yeah, I kind of fell into this, and now I'm on a journey of creating a better world for people with disabilities. So I started out just wanting to be a physician, just want to be a doctor, and I did start pre-med, and I was in the US military. But within 2 short years, I went from seeing the eye chart from roughly 10 feet away or more to now down to just 1 foot away. It was dramatic. I became legally blind from a form of juvenile macular degeneration called Stargardt's. And at that time, once you hit your 2200, it's supposed to plateau and stop, but mine never stopped. And so by the age of 21, I had to scramble for plan C, as I had to exit the military and exit my medical studies. So I chose engineering, and I struggled all the way through. I had the opportunity of working for some Fortune 500 companies, and so I immersed deeply into software engineering. But then within that journey, I ended up at the School for the Blind learning non-visual skills. So you can imagine. It was a very, very tough and challenging time. And then several years after that, I spent some more time at visiting all kinds of ophthalmologists, 300 of them. And we discovered that I actually have 3 genetic mutations affecting my retina. So that explained why I was having all the fluctuations and unstable vision. But all throughout this time, I kept thinking of how can I create something that could not only help myself, but also millions of people like myself. And so that's what threw me into neuroscience. That's how I discovered brain control. And now I'm on this journey of creating a better world for people with disabilities.
And tell us a little bit about the technology that you've created so far.
So Think and Zoom leverages the power of brain waves, but it does that non-invasively. So from a wearable BCI, which is a sensor that touches outside of your head. And just like Beata explained, we harness the electrical impulses coming from the brain. And we've been able to develop a prototype to show that it is possible to look, think, and zoom in to see better. So essentially, in layman's terms, you can now use your brain to influence magnification. So you don't no longer have to use your hands or manually control. You can now think and zoom in to see better.
It's brilliant. Fantastic. Beata, earlier this year, your boss, I don't know if we were able to call him this, but Elon Musk announced that a monkey could play with video games using its mind. This is kind of using the signals to control something external, like what you explained before. And while some parts of this technology are new, some of the applications of this kind of technology have been used for decades through devices like cochlear implants that were also starting to put signals, that were also used to put signals back into the brain as well. So Elon's also been known to say that BCI was integral for humans not to be outpaced by artificial intelligence. So it seems to be that it's one thing to get signals out of the brain to control an external device, but then another thing to, I guess, use those signals or to put signals back into the brain. So I guess my question to you is, what's the potential of this technology to put signals back into the brain, and what could that mean for people with disability? And also, I'd love you to mention some of the work that you've already done with another company through epilepsy as well.
Sure. So that's a very big question. But as you mentioned, cochlear implants provide a really good example of a very promising way to put information into the brain that the brain can then learn over not too long a period of time to make sense of and make use of for people with hearing disorders. Of course, the resolution of the input that you get from a cochlear implant is nowhere near the actual cochlea, but with the brain's plasticity, the brain has this amazing ability that if a source of input into it contains information about the external world that it's useful to the person or to the animal, it's going to learn how to make use of that information. And there's, of course, there's also visual prosthetics under development for, stimulating the visual cortex with a device like ours. And there's also, of course, retinal prosthetics, other things like that under development that are also very promising. As for, and you also mentioned with epilepsy, recording from, I used to work at a company called NeuroPace also that makes the RNS system, responsive neurostimulation. So it listens for brain activity, indicating that the person's about to have a seizure coming from the seizure focus, and sends some brief electrical stimulation to try to normalize that activity and prevent the seizure from progressing. And that also works tremendously well for people with medically refractory epilepsy. As for writing in the kind of information Elon is talking about, where you want to basically be able to do a Google search in your brain or be able to communicate with one another without having to speak, that's going to take, I think it's going to take a lot of either better understanding of the brain than we currently have, or a big leap in technology that I currently can't envision, but it is definitely a goal of Neuralink, a long-term goal.
That's brilliant. And Nick, just in terms of the work of Synchron, give us an update on kind of where things are up to now and what the next steps in terms of some of those human trials are going to look like.
Sure. So Synchron at the moment is, as you mentioned, continuing human clinical trial in Australia and branching out to the US. Our technology is a little bit different to a lot of the other existing brain machine interfaces in that we came up with a way where you didn't have to perform any invasive craniotomies, removal of the skull. You don't need to do that to implant our device to the brain, using blood vessels as the naturally occurring pathway to get to the different regions. So through a small incision, like an injection in the neck, we can put our device up and to the motor cortex, as Beata mentioned before. And once it's there, the patients can use their brain to think about activities that they would like to perform, and the device can obviously pick that up and wirelessly transfer those out of the body to be interpreted and used to control external equipment. I think certainly, for us continuing the clinical trial, when we started the company about 10 years ago, our vision really was to go beyond amazing research that everyone on the panel here is doing and get it into a product that can be used by people to help them with their lives and to help them and their carers perform different activities. So we're still on that pathway to start of a long journey. A lot of regulatory approvals and FDA testing and needs to be achieved, and certainly we're well on the way to getting a product out to those that can use it, with the idea being that for people who have through damage or disease a functioning brain but body that isn't connected, so they can't move their arms or limbs, spinal cord injury, for example, motor neuron disease or ALS in the US, and other different conditions that prevent the signals from going from the brain to their body. We're planning on helping those people and certainly trying to help them in a way that is surgically non-invasive, very minimally invasive, and can be used sort of out of the box to perform communication as well as other activities of daily living. So it's exciting, and there's a lot of people coming into the into this field at the moment, which is fantastic, and certainly I think there's a bright future for this technology and the people that will be using it, whether they be the users themselves or their carers or their families or whoever it might be.
That's brilliant. And I want to stay with you. Just you mentioned there kind of some of the regulatory pathways, and obviously this is all a journey towards commercialization and being able to have this available out in the market. And that you know, the $40 million of investment that you just got is people banking on you to be able to get something in the commercial market eventually. I want you to kind of just talk us through a couple of the kind of critical points on that regulatory journey so far. What did that look like? And yeah, I guess we've got other founders on the call today that are perhaps on a similar kind of regulatory journey. So give us a bit of a picture of what that's been looking like for you.
Sure. Well, certainly, you know, one of the main things you need to prove is that it's safe, and that, you know, that's for all technology, whether it's invasive, minimally invasive, non-invasive. You need to prove that it's safe and that the patients that it's intended for, you know, won't be put at additional risk by having this technology. And so that's one of them. And the FDA is obviously very big on making sure that there are a huge amount of tests that need to be conducted and shown to demonstrate that it's safe for implantation. And once it has been implanted, obviously the next step is to show that it works, that it's reliable, and that it can perform how it's intended to perform, and allow the user to communicate with it, for example, if that's the goal, or to control a prosthetic limb or whatever that might be. So there's a lot of work, you know, in the background. Once you've made the technology, and even once you've got the surgical procedure right and implanted it, there's a lot of work that needs to go on in continuing to demonstrate and prove that it's safe and functional and will continue to be reliable over the lifespan of the patient. And I think one of the things that's amazing is with all the technologies that brain machine interfaces seem to be achieving is getting commands out of the brain, and what happens at the other end. There's a lot of work also going on, you know, how you can make better technology that allows people to use these devices properly. So making robotic limbs and making exoskeletons and wheelchairs. There's a whole range of other applications that people can use that they're only starting to be built as well, which is fantastic. So it means, you know, the people that are making the implantables now have a lot more things to connect to, so the users can control a lot more of their environment.
That's super interesting. Yeah, thinking about the kind of marketplace of available technologies that might need to be there in the future. Zuby, for you, the regulatory environment's kind of a little bit different for those kind of intracortical devices, so ones that go inside the body, versus those using neural decoding like EEG. So you might want to give a little explanation of EEG, but what have been some of the significant milestones in your own commercialization journey?
Yeah, like Nick has, given details. The intracortical is a very heavyweight regulation, right? Because it's going into the human body. But for the EEG, which we're leveraging a head wearable device, so it doesn't go into the human body. So we're not looking at that, length of time and all those lengthy clinical trials. So we envisage it's going to be shorter. And in terms of some of the milestones we've achieved, well, we've gone from just concept, an idea, to various prototypes. We have a prototype that runs on a smart glass, which is what we envision in the future, something very lightweight and portable that you can just wear. We also have a version that works on a smartphone. And in the future, we hope to add one that works on your laptop. And we also, in order to lower the barrier of entry, because people, as you can imagine, ask a lot of questions about, is this real or something else? We created a game out of it that fortunately won an award at Apple Worldwide Developer Conference. So it's a brain controlled game. And we also earned a patent. So these are some of the milestones that we've achieved. But we also do face some barriers and challenges as most investors still do not understand the disability landscape very well. And so these are still some of the things we're trying to tackle to move forward.
Yeah, that's brilliant. We've had a question come through on the chat asking, are these devices suitable for people with cerebral palsy? So either Nick or Beata, do you want to take that one?
Yeah, I think I can start and I'll pass off to you, Beata. I think in general, yes, but it really depends on the type. You know, certainly for the Stentrode and the technology we're developing in the first case, provided they have a functional brain, and that meaning that they can think and cause the cells that Beata was talking about before to function. It doesn't have to be everywhere, but just some of their brain can respond normally, and that they can have intentional thoughts. Then yes, you can acquire these, and they can be used to assist. But I suppose that there are going to be some conditions where parts of the brain responsible for arms or limbs may not work. That might be okay. You might not need that specific region to be working, but certainly, you know, I think it's a case by case sort of scenario where their physicians will be able to assess whether this is something that would be suitable for them.
Yes.
Yeah, I think Nick stated it perfectly. Just if you know the part of motor cortex that controls movement is still responsive in a way that communicates the person's movement intent, then these kinds of devices could be used. Or some part of the motor system, doesn't necessarily have to be cortical. But as long as movement intent is still represented in neural activity, then something like this could work.
Awesome.
And
well, we encourage you to put some.
Oh,
yeah.
Sorry, to add to that, that's for brain machine interfaces and brain control. And if there are other issues with other parts of the body, there are technologies, many people around here as well that can directly be involved with the damaged limb or the part of the nerve in the limb or something like that. So it doesn't necessarily need to come from the brain, and there's a lot of other groups and a lot of other research and work that's going on to look at how you can really replace anything that's lost or damaged, and so the field of biomedical engineering is certainly taking off, and I think there's unlimited possibilities in that regard.
Yeah, we've seen some incredible research happening at Brown University where they're essentially taking signals from the spinal cord and looking at reinserting those essentially back into a damaged spinal cord below where a break might have happened. So it's just, there's an incredible kind of forefronts, I guess, for so much of this technology. Control Bionics is another organization here in Australia that's done some work around taking any kind of signal from a muscle and being able to turn that into a control button as well. I guess I wanted to, and this one we might, so I encourage people to put questions that they've got into the Q&A panel down below. We'll try and get to as many of those as we can. One of the questions I did want to ask each of you is if you could just briefly touch on what are some of the ethical questions that you think that we should be asking ourselves in this work? Do you want to start with that one, Zubi?
Sure. In terms of ethics, right? I think we always have to remember that the piece of technology is to serve the human, right? And we always have to do our very best to put the human first. And then in trying to do that, we have to look at the cross section of humanity. And it pinches me to even touch on this, is the event that happened at the Paralympics, right? Where the blind athlete was hit by a self-driving train because that wasn't considered. And so if you think about the Paralympic, that should be the haven for people with disability, right? Everything disability should have been covered. but then the self-driving train, which is great, but then this one angle wasn't covered, and it was disastrous. So I think in terms of ethics, rather than even trying to think too hard, just remember, no matter how great the technology is, A, we're trying to serve humanity first. And then B,
Right.
let's look at all humanity and be inclusive. So that's my take on that.
It's brilliant. Thanks, Huvi. Piata.
Yeah, and just to add on to that, I guess I would say another thing that needs to be thought about carefully is the fact that a lot of these technologies right now are meant to be assistive for people with disabilities, restoring function. But now and then also going forward, if these ever become kind of enhancement technologies, making sure that they're available to everyone, not just people that are wealthy. Make sure that your insurance model includes, Medicare or Medicaid or whatever, just to make sure whoever needs them is able to get them.
That's brilliant. Thank you. Nick.
Yeah, look, I think what Zubi and Beata said is spot on. We got to really make sure, as everyone who's working in this field does, that we put the patients first and we really have their best interest in mind. I think there are a lot of ethical issues, like you mentioned, that haven't been thought of, Zubi, and yes, certainly time needs to be spent making sure that all bases are covered where possible. But there are new things that arise as new technologies arise, and I think as long as the researchers are aware and continue to be motivated towards helping the human condition, then I think we're in a good place with people like this on the panel who are in charge of this sort of tech.
So one of the questions has come through, a little bit more of a technical question, or a couple of these are. So how does your technology deal with signal noise, and particularly for the intracortical devices, so those inside the body, the signal loss over time due to local inflammatory response? So you might just want to give a little bit of context about what happens when we put foreign objects inside the human body. And I know Nick and Beata, you'll have different responses to this.
I can start that one off. So at BrainGate, we've had participants that were implanted for over 5 years, in whom the device was still working well enough that the neural signals weren't quite as beautiful as they were in that example neuron that I showed you guys earlier. But we can still get information out of the residual signals, even though there's a little bit of a gliosis response, where the glial cells, that sort of the glue that holds the neurons together in your brain, tend to kind of wrap around and protect the rest of the brain from these devices that we've implanted in them. It makes the signal a little bit smaller over time, but it's still possible to get useful information out of them. What else was I going to say? Oh, and at Neuralink, we're working on ways to make the response, this immune response, kind of as minimal as possible. And one way we're doing that is by having very, very flexible electrodes that they get put in with a very tiny needle that's a quarter the size of a human hair. The needle's taken back out, and then these tiny little flimsy things that you can't even really see with the naked eye end up staying in the brain. They move with the brain. They're a little bit more invisible to the brain. They can be coated with molecules that the brain recognizes as good things and have the brain kind of accept them more easily that way. So these are some of the ways in which we're dealing with that. And yeah, I'll pass it on to Nick.
That's great. Nick, what about you?
So our stories are a little bit different. When you put things inside a blood vessel in ours, so our device, it goes in through a blood vessel through a very small sort of sub-millimeter catheter, and when it's in the desired location, the motor cortex, then we remove the catheter and it expands to put the electrodes or the sensors against the vessel wall to allow blood flow to go through the middle. What we found is a process of endothelialization, or the gliosis, the body's response to devices. In a blood vessel, it'll push it away from the inside of the blood vessel, so the device gets incorporated into the vessel wall. What we found, both in the preclinical trials and the humans, is that that's actually beneficial for us. The device gets incorporated into the vessel wall, where it sort of anchors, and so our signal to noise improves, because there's no movement through the middle, and the device is more stable. So fortuitously, we've found that the body's reaction is actually helping our signal quality over time. And once it reaches a point, obviously, where it's incorporated in the vessel, within a couple of weeks, then the signals, remain. And we haven't got to 5 years yet. Our first patient was in August 2019. So only 2 years down, but certainly we've seen that the signals remain as they did at the 2-week point from then on.
That's brilliant. And certainly go have a look at some of the videos, both of Neuralink and also Synchron, for kind of seeing some of the things that both Beata and Nick have just mentioned. Another technical question, well, they've called it a slightly technical question from Dimitri from ThoughtWide. How high or low do you think that the ceiling for EEG-based BCI is functionally, especially with devices that are wireless and easy to wear versus those that are lab grade caps with amps they've talked about? So again, maybe just give us a little bit of context for those that can't imagine the technology that's just been mentioned there. Who wants to take that one?
So
do you want to take that one? Nick, you go first.
Yeah, I've got a comment. I think that there's a lot of different technologies that will have different benefits to different patient groups. Obviously, if you're placing something outside the skull, the skull will act like a filter and will suppress some of the activity that you get. But that might be fine if you only need to have a binary switch to control some applications. Then that's one application. Certain people might have that. And indeed, some of our patients haven't wanted to use all of the electrodes or sensors we've got in there. They're happy with just getting really good at one or two sensors or clicks, if you will. And they've found that even with those, they can do a huge amount of communication and web-based activities like shopping and banking and financial management. And they've said, that's enough. I don't need all these other switches for me to, for them, that person to have benefit. And then you go to Beata, where they've got many more electrodes and sensors, and certainly again there'll be different applications for that. There are going to be people that want to control a huge amount of information, whether it's receiving or sending. And so I think a lot of this technology will have a base level of everyone will be able to do this, but there'll be certain subsets of individuals as well as different conditions that might benefit from each way of addressing the same problem.
So do you want to have anything to add to that?
Yeah, I might just add to that. I think Nick is right in terms of the different areas of applications. But that question also made me remember one. I think it's out of MIT Media Lab. It's called Alter Ego, where they actually take the signals from the throat area. They tap electrical signals before your voice box actually issues the sound. So you're silently whispering to yourself. So again, that's another way of grabbing electrical signals out of your head.
And then we're kind of running short of time now, but one other question that we've got there in Q&A is, do you feel it will be disability assist or performance enhancement that will be the primary driver of BCI progress in 5 to 10 years' time? So Beata, do you want to take that one first?
I think definitely starting with disability assist. That's been the big driver all this time. And the fact that it kind of remained in academia for so long, that sort of the intracortical brain computer interface, at least, kind of speaks to the fact that there hasn't been as big of maybe a push from the disability community, or I don't know why. It's just kind of stayed in academia for so long. But then it's been nice that there's been much more kind of commercial interest in bringing it to market. And I think definitely the fact that it's going to take that stop along the way is a great thing for the disability community. And then whether or not it actually ends up in the enhancement stage, I'm a little bit skeptical. there are certain things that I think we definitely can do in the near future, like, you know, add sensory modalities, for example, that for things that already exist, like which way is magnetic north, or like seeing into the ultraviolet range or something like that. Yeah, as for like writing in really complex information, I think that's going to be a little bit harder. But definitely, like one of the drivers of both the enhancement and the disability technology is trying to get to that final enhancement stage.
Zubi, what about you?
My hope is that we can start out focusing on the disabled. There are 1 billion of us around the world, and largely overlooked, right? And you can start looking at the statistics and all kinds of data. So that's just my hope, that we can finally focus on this group of people and get them to climb out of the very ultra high unemployment rates and poverty rates, and get them to learn and earn so they can become economically independent and contributing members of society. And you can never really say never, right? We don't have a crystal ball of what will happen 5, 10, 15 years from now. Maybe the performance enhancements market will kick off, but my hope and my prayer is that for now, let's leverage what we have and help those who are in need.
That's awesome. Nick, what about you?
Yeah, look, I agree. I think certainly if you look at what's happened in history with let's say plastic surgery, which started as a medical procedure for burns and other reasons. Once it got traction with the medical community, then obviously the larger community have taken that up and spun it in their own way. And I think you see the Paralympic Games that were just on, and certainly a few years ago, you may recall the Blade Runner, Oscar Pistorius was wearing sort of bionic limbs, and wow, that guy was fast, like certainly much faster than I was, probably equally as fast as some of the athletes that didn't require prosthetics. And I think they had to slow the legs down so he didn't go too quick. But I think you'll see a time where some of these bionic replacements are better than our own limbs. Some of the arms that have been made by in the US are arguably better than the one I've got now. So, I think there is going to be a time where where the technology, excuse me, improves people to a level that they're not at yet. But I can't see that. I certainly want to see that happening for the people that need it in the first case, and I imagine that's where it'll start.
That's brilliant. Well, the last question that I have for each of you, and we'll have to keep this brief because we're just about out of time, but what's one remarkable insight that you have for BCI generally and where it's headed? So Beate, we'll start with you.
I'm not sure I would qualify this as a remarkable insight, but my own personal insight is just kind of my story of like how I got started in neuroscience was because I was very interested in consciousness and how brain activity gives rise to consciousness. And it's an inherently subjective thing, so it's very difficult to study. But now that we're making these brain-computer interfaces and implanting them in human study participants, maybe we have a way to actually start accessing some of these questions as well, because now we can actually introspect and see what kind of neural correlates there are of these subjective phenomena.
That's fantastic. Nick?
I think the insight that I'd like to share was from our first participant when he was using the system. Firstly, it was absolutely magic to see a man sitting there paralyzed controlling something on the screen. But the thing that I didn't appreciate at the time was the people that benefit from this aren't necessarily the users only. So he was obviously benefiting. He was able to control his environment, but on the side note, his wife and carer, she was able to get more independence, knowing that she could now leave his side to go out in the garden, go down to the shops. We connected him up with communication tools, WhatsApp and texting, so that they could always be in contact, but she didn't have to be there. And I didn't appreciate at the time and when building this, the impact that would have on the carers and the family and the people that aren't necessarily the recipients of these sort of technologies. So I think that was a big insight for me, and certainly, you know, lovely to see that what we're doing is more further reaching than the users or the people that actually receive the tech.
Absolutely. Yeah, there's the also under-recognized support community and carer community that happens alongside some parts of the disability community as well. So that's brilliant. Zubi, we'll finish with you.
Well, I think my insight will be the moment. So what I mean by that is, I mean, look at the team you've assembled here, right? These are folks at the bleeding edge, pushing technology forward to help humanity. I think this is the right team to do the job, right, and create positive impact. But then also the forum. This is probably one of the first times Remarkable Insight has put together a BCI, right? And so that's great. It's an exciting moment. But then look at the humanity, the disability space, from Caroline's amazing job of developing 500, and I just happened to be in Geneva, Switzerland, to echo her message same year at the UN. And now 2 years later, we do have those 500 companies, and you move over to We the 15, right? And then we move over to Plus IN, Inclusive Innovation Network. And then there's Think and Zoom Future of Disability with a list of global innovators. So that's what I mean by this is the moment, right? So we are pushing forward the technology, and we're also bringing the humans together. And so this is the moment to bring it all together.
That's really exciting and really well said, Zubi. Thank you. Please join me in thanking our panelists today. We've had Beata, Nick, and Zubi, also to Taryn, our Auslan interpreter. It's been fantastic having a conversation with you. Remarkable is about harnessing technology to build social, economic, and inclusion, and so for people with disability. So we want to welcome anyone to express interest in our accelerator program that is open right now for our accelerator program running in 2022. Today is also Are You OK Day in Australia, and Are You OK Day, while we're waiting on technologies like BCI that might actually be able to assist people who, those of us who do have mental health challenges, one of the things that we can do right today is to check in with people that we know and love, and to check in and ask if they're doing okay. It's important that we look after ourselves in this time of need as well. We'll be seeking some of your impact on today's Remarkable Insight session as well, so if you could leave some comments straight after this webinar, that would be fantastic. The recording will be made available as well on Remarkable Tech's YouTube channel. Make sure you subscribe to that. This kind of conversation we think is vital. Like Zubi said, we hope that this moment in time of the bringing together of people, technology, and where the future of technology and innovation is headed is going to be more inclusive. And so we thank you for joining us for this Remarkable Insights. We look forward to you joining us for the next Remarkable Insights during Spark Festival next month. Enjoy the rest of your day, wherever you are calling from. Good evening, good morning, and good night.